Hello guys, today is the day 5 of second week and today I'm gonna और आज मैं सिस्टम डिज़ाइन पढ़ना स्टार्ट कर रहा हूँ जो मैंने टेक्निकली कल ही कर दिया था बट या दैट इज़ ऑल्सो इम्पॉर्टेंट। डीएसए के साथ में सिस्टम डिज़ाइन भी करना पड़ता है एंड नॉट जस्ट सिस्टम डिज़ाइन बट ऑल्सो डीबीएमएस एंड कंप्यूटर नेटवर्क्स एंड आई एम गोना डू दैट लेटर। I'm gonna do both of them later, but अभी तो I'm gonna start with system design। कल मैंने पहला लेक्चर देखा which was an introductory video and I also found a striver sheet on system design, so I'm gonna follow that and yeah, okay, now I'm gonna start today's stream.
Basics of system design. If you have never designed a system before, this is probably the place to start. So imagine you have a computer with you in which you have written an algorithm. So some code is running on this computer. And this code is like a normal function. It takes some input and it gives out an output. You expose your code using some request, there's a corresponding response that your computer will be sending back. Imagine setting up this computer. It might require a database to be connected to it within the desktop itself. You might require to configure these endpoints that people are connecting to. And you also need to take into consideration what happens if there's a power loss. If someone pulls the plug or something like that, you cannot afford to have your service go down because there's lots of people paying money for you. You should host your services on the cloud. So what's the difference between a desktop and a cloud? Nothing really. The cloud is a set of computers that somebody provides to you for money, of course. So if you pay a cloud solution, for example, Amazon Web Services, which is the most popular one, if you pay these guys, they're going to give you computation power. Computation power is nothing but a desktop that they have somewhere which can run your algorithm. How will you actually store your algorithm in that desktop? Well, you can do something like a remote login into that desktop. That's what the cloud is. It's a set of desktops, not necessarily desktops, but a set of computers that you can use to run your service. The reason we like to do this is because the configuration, the settings, the reliability can be taken care of to a large extent by the solution providers. So now that we have our server hosted on a cloud, which is basically some computer that we don't know about, we can focus on the business requirements. What business requirements could we possibly have? Well, there's lots of people who are using algorithm now. and it gets to a point where the code that you have running on the machine is not able to handle all of these connections. So what do? One of the solutions is to buy a bigger machine. Right, this is solution number one. The solution number two is to buy more machines. The ability to handle more requests by buying more machines or buying bigger machines is called scalability. More requests by buying more machines or buying bigger machines is called scalability. This is a very important term that we need to understand well. Like we said, we can handle more requests by throwing more money at the problem. When you're buying bigger machines, it means that your computer is going to be larger and therefore it can process the requests faster. So that is called vertical scaling. And when you're buying more machines, it means that the request can fall on any one of these machines and it will be processed. But because you have more of them, the requests can be randomly distributed amongst the machines that you have just bought. And that is called horizontal scaling. These are two mechanisms by which you can increase the scalability of your system. Like we said, scalability is being able to handle more requests. Like any two approaches, we can compare them with the pros and cons. The first one that we have talked about is we need some sort of load balancing here. Well, that's not the case here. If you have a single machine, there's no load to balance as such. The second point is that with lots of machines, if one of the machine fails, you can redirect the request to the other ones. While over here, there's a single point of failure. So this is a single point failure. And here it is resilient. The third thing to note is that all the communication that we have between the servers will be over the network. And network calls are slow, it's I/O. While over here you have inter-process communication, so that is quite fast. So here there is inter-process communication, while over here we have network calls between two services. So that is remote procedure calls. So this is slow and this is fast. The fourth point is data consistency. For example, let's say you are having a transaction where 3 sends some data to 4, and then 4 sends it to 5, and 5 sends it to 1. Here you see that the data is complicated to maintain. If there is a transaction where the operation has to be atomic, what could happen is that we have to lock all the servers, right, all the databases that they're using, which is impractical. So usually what happens is we have some sort of loose transactional guarantee. And that's the reason why here the data consistency is a real issue. While over here, there's just one system on which all the data resides, and that's why this is consistent. The final point deals with some hardware limitations that you are going to have, because we cannot just make the computer bigger and bigger and bigger and solve the problem. There's going to be some hardware limit that we have here. It's point number 5. And over here, this scales well in the sense that the amount of servers that you throw at the problem is almost linear. In terms of how many users are added. These are the 5 key differences that vertical scaling and horizontal scaling have. So what do you think is used in the real world? Both. We take some of the good qualities of vertical scaling, which is really fast inter-process communication and the data being consistent. So the cache is going to be consistent. There's no dirty reads, dirty writes, so to speak. We take these 2 good qualities from here, and we take these 2 good qualities from here, which is it scales well because there's a hardware limit over here, and it's also resilient in the sense that if one of the server crashes, somebody else can come up. Okay, so the hybrid solution is essentially horizontal scaling only, where each machine has a big box. I mean, each machine you try to take as big a box as possible as feasible money-wise, and then we pick up a solution this way. Initially, you can vertical scale as much as you like. Later on, when your users start trusting you, you should probably go for horizontal scaling. So these are the major considerations we have when designing a system? Is it scalable? Is it resilient? And is it consistent? With these qualities, there's always going to be some trade-offs that we have, and that's what system design is. We design a system which is going to meet the requirements, and the requirements are such that it's going to be computer science ways possible to actually build a system like this. If you have any doubts or suggestions, you can leave them in the comments below. If you want notifications for further videos, hit the subscribe button, and I'll see you next time. This video is on the basics of system design. Hey everyone, today we are talking about estimation questions. These are useful in design interviews and also in general. Let's take an example. What is the total amount of storage YouTube needs per day? So I'm assuming that there's 1 billion users that YouTube has. That's 1 billion. And how many of them upload videos? Well, maybe 1 in 1,000 users. Okay, so these are the number of users who are uploading videos. Each video, let us say, is around 10 minutes long. What's the size of the 10-minute video? 2-hour movie is usually 4 GB in size. And expect YouTube to break this down to low quality because you're not selling those videos anywhere. So 0.4 GB, that is 400 MB for 2 hours. You get around 200 MB per hour of video footage. So let's use this number. You have the total number of minutes being expressed by this number, which happens to be 10 raised to the power 7 minutes and 200 MB per hour. So that is 200 by 60 MB per minute. So 3 MB per minute. The total amount of data you need here is 10 raised to the power 7 per minute. So 3 MB per minute. The total amount of data you need here is 10 raised to the power 7 into 3. 30 terabytes of data is required here. So this is the approximate amount of storage you need to just keep raw footage of YouTube on your storage disks. But this is just one copy. So if someone uploads a video on your platform and you just have one copy and you get some sort of a tsunami in that area where you had the data, you lose it, right? So you want some redundancy, not just for fault tolerance, you also need it for performance. Like if you have a copy in India and a copy in the US, they're on the opposite sides of the world, it's a little easier for users nearby to use that copy. It's faster. So I'm going to keep 3 copies. I'm going to assume 3 copies for fault tolerance and redundancy. So that is 90 TB. And you don't just keep it in one resolution. You want to keep it in multiple resolutions. So for example, if I upload a 720p video, then I want this in 480 also. I want it in 360, I want it in 240, and I want it in 144. Now each of these sizes are smaller. So this is like half of the original requirement. If this takes, let's say, X MB, then this takes X by 2. This takes X by 4, X by 8, X by 16, right? So putting them all together, you'll get somewhere around the total. If you do the total, it's going to be around X MB itself. So twice of this 2X storage is required if you want to store it in all the resolutions. So whatever my original storage was, 90 TB, I need to double that. I get 180 TB. And so in point around X by, if this takes 4 itself, this in tolerance and redundancy, so that is 90 TB. And you don't just keep it in one resolution. You want to keep it in multiple resolutions. So for example, if I upload a 720p video, then I want to say 40 resolutions. So whatever my original storage was 90 TB, I need to double that. I get 180 TB. And so in 0.18 or 0.2 petabytes, basically, I can store all the footage I need for one day. There's a lot of assumptions I made here, and it's best to keep looking at the interviewer in case they feel like some of your assumptions are complete nonsense. For example, the number of uploaders. If you can get this number from them, it's great. And then you have the total number of minutes per video. This makes sense. 10 minutes is fine. The big assumption over here again is that instead of 4 GB required for 2 hours, I'm making 0.4 GB. The assumption here is that the quality of the video is going to be lesser, and also using some sort of machine learning, you can bring down the quality significantly, but it may not be the case. This can be up to 4 GB, which basically makes this 2 petabytes. Yeah, so it'll be an order of magnitude away. So just be aware of the assumptions you're making, and also clarify that this is how you're coming across the solution. The important thing is not the numbers. The important thing is how we came across and built this solution. If you're off by a factor of 10 or even 100, actually, it's okay. Like 100 is a bit much, but it's okay. But if you're off by a factor of magnitude of 3 or 4, that is like 1,000 or 10,000, then there's something absolutely wrong in the calculations, and maybe we can do some improvement. The other thing that I'd like to bring your attention to is that the more accurate numbers you have, the more close you are to the original solution. For example, I kind of made an assumption over here, 2 hours is 0.4 GB. I could also think of one video being a collection of images. So instead of using this assumption, I would say, what's the amount of memory you require? What's the size of a 1 minute long video? And 1 minute is 60 seconds. The number of frames you have per minute is 24. And what's the size of an image in this? Because it's like a collection of images, right? A video. This is equal to the length of a 1 minute video. That turns out to be, if an image is of good quality, that is 1 MB. Okay, so 1 MB into 24 into 60. I'm going to make this as 25 because I'm approximating anyway. So 1500 MB, that is 1.5 GB per minute. Now you can see that 1.5 GB is very, very far from 3 MB. And the reason why this has happened is because I had a completely wrong estimate on the size of one image in a video. Of course, this is exaggerated just to prove a point that if you have to break it down, you have to make more assumptions, and usually it turns out worse than the other answer. Let's continue with the example. Let's say that let's continue with the example. Let's say that you have all these videos and you want to cache some of the metadata that they have. So what kind of metadata would you like to cache? The things that are visible to the user, yeah, in a list when you give them a recommendation or on the trending tab or wherever. You have the thumbnail that you need to show, and you have the title of the video. Now take a quick guess which one is going to be heavier. It's the thumbnail because it's an image. So the image can be at most 1 MB, but of course, when you want to show this to the people, you're not going to show it at full 1 MB resolution. You instead want it to be much, much, much smaller. So I'm going to assume that it's going to be, let's say, 100 times smaller, because it's like 10 times smaller than the original image from both sides. So this is going to be 1 MB by 100, comes out to be about 10 KB. Okay, so 10 KB of storage is what you need in the cache for your thumbnail. So 10 KB into the number of videos that you upload in a day. Not really, because what you want to show are popular videos. You want to cache the popular videos. The popular videos are approximately the last 3 months videos, and also ever green videos. Okay, so and how many of them upload videos? Well, maybe one in 1,000 users. Okay, so these are the number of users who are uploading videos. Each video, let us say, is around 10 minutes long. What's the size of the 10-minute video? 2-hour movie is usually 4 GB in size. And expect YouTube to break this down to low quality because you're not selling those videos anywhere. So 0.4 GB, that is 400 MB. It's a little easier for users nearby to use that copy. It's faster. So I'm going to keep solution. The important thing is smaller because it's like 10 times smaller than the original image from primarily because whenever you need to retrieve some data in the cache, you want it to be routed to the right place. I don't want to be searching amongst 32 GB of RAM where my thumbnail is. So instead of doing all that, I'm just going to be routing it to the right processor and using basically more computers. If I use 32 GB, of course, the denominator is increasing, so I'll have to use lesser nodes, but 16 GB is what I'm going for. So this turns out to be, in terms of GB, this is 1000 GB divided by 16 GB per node. So this comes up and we have 64 nodes in your cache system. If you're looking for any kind of redundancy, which is good to have because you need to serve the videos all over the world. And also if any of these nodes crashes, then there's going to be something like a cascading failure because you're at your peak capacity, all the nodes are being worked at peak capacity, and if any one of them crashes, then the work on the other nodes will increase. So I don't want that, and I'm going to keep that around 50% capacity. Rough estimates are fine. This is approximately 500. So with 500 nodes, I'll have a caching system, each with 16 GB, I'll have a caching system which should be enough for YouTube's metadata. You need to process 10⁻⁷ minutes of video in a day. It's equal to the amount of video that is being pumped in. You have to pump that much video out. Currently, this metric is not making much sense because this is telling you something in terms of time, and this is telling you something in terms of time again. What we want to know is how much MB can we process per second. Yeah, computers usually talk in terms of nanoseconds, milliseconds, or seconds. 1000 into 10⁴. This is 10⁴ divided by 3 hours. 10⁴ by 3 GB of video to be processed in a day. But how much is that in seconds? So this has to be divided by the number of seconds you have in a day. Cancel these terms out, you have 40 MB of data to be processed per second. This is an important metric for us because our computers, when we talk about their processing power, we say that this is the amount of data that it can process in a second. So if you take a computer and you think about processing video through it, what's going to happen is 3 steps. First one, it needs to read the video into memory. So that is a read operation. The second one is it's going to be doing some sort of image processing or video processing. So I'll just call that processing. And the third one is it has to write it back into some place. Now 40 MB per second is the raw footage. But if you're doing multiple formats, like we said, and multiple places, so in 3 data centers, that's going to be something like into 10. So I'm going to just bump this up to 400 MB per second worldwide. This is the amount of data that you're working with. To read a single MB of data from disk takes you about data centers. That's going to be something like into 10. So I'm going to, if you're doing multiple formats, like we said, and multiple places, so in 3 data centers, that's going to be something like into 10. So I'm going to just bump this up to 400 MB per second worldwide. This is the amount of data that you're working with. To read a single MB of data from disk takes you about 10 milliseconds. Plus the processing time is something we'll have to assume. And a write, I'm assuming to be twice the amount of time required for a read. As I said, it's an interview. You can make assumptions. As long as they're sensible, they're going to be accepted. So 20 ms write speed, 10 ms read speed, and processing, I'll just put that to be 20 ms again. IO operations are usually slow, so this makes sense. You have 50 ms. You need 50 milliseconds to process 1 MB of data. And you have 400 MB of data per second. So effectively, you have 400 into 50 into 10 raised to power minus 3. So this is in seconds of work to do per second, which turns out to be, if I remove these 3 zeros, then this factor goes away, and you have 20 seconds of work to do per second. So 1M. This is the total space requirement in my cache. So you have 90 days, and I'm ignoring all the evergreen videos because it's going to come into this only. It's going to be a LRU kind of thing. So 1M. This is the total. Seemed like a small number, and to be honest, I might have missed out on some factor over here, which is an interesting thing. If you find it in the comments, you can tell me. So what we have done here overall is taken an estimation question and tried to bring it down to our level. Initially, we had what is the total amount of storage required by YouTube. Instead of answering that through a guess or by reading a lot of articles, which is really difficult, what we did is we saw the amount of data being pushed into YouTube. This is a guess per day. That is a metric we took. And then we brought it down to seconds, something that we are comfortable with, because a computer speaks in terms of the read and write times in milliseconds or seconds. So this is a big assumption. You will be judged probably on this kind of assumption. And if you have numbers which are completely off, let's say 1 second or 1 nanosecond, that's a red flag. So there are some numbers that everyone should know. There's a slide which actually says that. And just go through that slide, go through the links in the description. If you like the video, then make sure to hit the like button. And if you want notifications for further videos, hit the subscribe button. I'll see you next time.
So, like I was telling you guys, the OSI model is more of a reference, a guideline to help us delegate responsibilities, to help us understand what the communication process entails. And so I had you guys just list them out from top to bottom. But remember, the communication process entails both directions. Going down the stack is what we call encapsulating, and going up the stack we call decapsulation. And today I hope to explain why the encapsulation process is very critical to the communication. That is, to get the message from the sender to the receiver. Layer 7, layer 6, and layer 5 can be grouped in. In fact, the sole responsibility for the three of these is to produce what for the transport layer? Yeah. So by the time we get down to the transport layer, the PDU should look something like this. It should be two or more devices connected to the network, sending what a 9 volt, if I asked you what a 9 volt, but they're physical. So they said the first three layers are going to be accomplished under the application layer. So I just grouped the first three. In fact, when we looked at layer 7, 6, and 5, didn't I say that's all software stuff? OSI model is a little bit more thorough and said, you know what? I don't want a cryptographer writing the user interface for my web browser. And thank God for that, because if the cryptographer did do that, they would hide the OK button. It's a secret. Likewise, I wouldn't want a programmer who develops user interfaces to write the cryptography program, because they would say, oh, it's real easy. Password's password. Because their job is to make the application user-friendly. The cryptographer's job is to make it very unfriendly, so that when you see it, it doesn't make any sense.
Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be talking about the TCP IP model. Quick warning, we're going to be referencing the OSI model a lot here. So if you haven't already watched that video, check that out first, then come back. Okay, so what is the TCP IP model? It's a model to standardize computer networking. Sound familiar? It should, because it's the same description as the OSI model. Now, the OSI model, while widely referenced, isn't used in the real world. The TCP IP model, however, is the real deal. Thankfully, it's not that different. Here is the TCP IP model. 4 simple layers: application, transport, internet, and link. And just like the OSI model, it's numbered from the bottom up, but the direction depends on if you're sending or receiving traffic.
हेलो एवरीवन, आज के इस लेक्चर में हम लोग डिस्कस करेंगे टीसीपी आईपी मॉडल को और टीसीपी आईपी मॉडल का क्या यूज है, क्यों हम इसको अडॉप्ट हम लोगों ने किया है, और टीसीपी आईपी के जो 4 लेयर मॉडल हैं उनको डिस्कस करेंगे विद देयर जो
I've got a pop quiz for you. What database system has been around for almost 50 years? I guess you can guess it by the topic of this video. It's a relational database. Hello, my name is Jamil Spain, developer advocate with the IBM Cloud and brand technical specialist. In the U.S. financial services market. In today's talk, we're going to dive a little bit into relational databases. I'm going to get into some of the characteristics of the database model and also some benefits that it provides for you when making your decision that you want to use this for your next project. To get started, let's talk about the structure of a relational database system. It's going to pretty much map out your data points and bring out the relationships in that. And the way that it accomplishes that is through the first thing is making tables, which represents particular items or nouns or particular entities of your particular system that you want to actually prototype. So let's say I have a bunch of books. Now this is going to be a table. It accomplishes the attributes of these books by having columns. And columns will be things like name, date, okay, maybe author. Of course, got to have an author for a book. And every table is going to have an ID field, some way to uniquely identify it. Each row of this database table represents an actual record or an item, a type of book. That's how it really fulfills that ability to hold the database system there. And then the way you kind of query out this particular system is through what we call a SQL, a structured query language. And it's a particular system you can say, select all the books and give me all this data out for me to use. Now we have one particular item here, books, but where it really comes, you really see the power of a relational database. Let's say now I want to show the authors. And the way that relational databases can really provide the structure of relating these two entities together is by describing them through particular entity relationships. You have one that you'll hear about where books can have multiple authors, so maybe a one to many. You can have a 1 to 1. And these are just a couple of relationships you can kind of mirror within the database system. So one way that I can have this kind of a normalized structure is to say definitely the authors is going to have its own particular ID and name and any particular order of attributes that I want to describe there. But I can also, one of these fields can be an actual number that actually relates to the ID of this field. And this is what's known as a foreign key. And of course, there'll be a name there. So when I do my query, the next query I do, I can reference both these tables and say, hey, give me all the books and give me more of the author information from this table using this foreign key to describe that particular structure there. Now you can imagine you'll be running a lot of these queries a lot, and there are some benefits or some things that are provided to help with those, to speed up these queries and make them operate as efficiently as possible. You have the database will provide ways that you can kind of set an index. Let's say that I'm often querying and always trying to pull out by name or by date. I can set an index on this particular column, which will automatically index all the values. So the next time you run this query, it's going to pull from what we like to call this cache of all the values. Most importantly, every time new rows are added, records are added to this particular table, the index keeps building this recent, I like to say cache of all these values, so it's always keeping up to date to work there. So this is all the characteristics of what you kind of have to model out your particular application that you want to build and describe how the entities are related to each other. Now let's switch over here to some of the benefits that you're going to get out of the box with a relational database that you want to use. The first we'll talk about is the consistency. Now this is useful because let's say there's some point where I want to run multiple of these transactions. Let's say I'm modeling an inventory system for an e-commerce application, and I have the need to write several queries in a row that may manage a couple of different subsystems. But if one of those queries fails, I want the option to be able to roll back the whole set of all those queries just to make sure that my data always maintains some consistency there. The second is the option to do stored procedures. Sounds like a very complicated word there, but think of stored procedures as the ability to write multiple blocks or functions of code, or if there are a certain amount of queries that I continue to always run, I can kind of model these so it takes me less code to write that particular, to access that same functionality with less SQL code. And as you start to get into more SQL writing with relational databases, you'll see queries can get pretty big. Another way you can do this as well is another topic called views here. Definitely want to introduce some of these keywords. As you do your deeper dive, you're able to see a lot of these and it be familiar to you. And the last one is a mechanism to handle locking in the database and concurrency. Why is that important? Well, at some point, multiple users are going to want to use the database maybe at the same time. Maybe two applications are going to be adding in books. And if the first application is making a particular insert into this table, you're going to want to make sure that the database is locked until that write is done. And then the second application has its ability to go ahead and make its insert as well. So these are all built into a lot of the relational databases that you'll use. A lot of these benefits will be provided for you out of the box. Not necessarily something you'll have to write in code, but just know that you'll have this at top of mind when you are kind of selecting to use a relational database for your next project. I hope this is good for you to understand the foundation of relational databases. Talk to you next time.
If you have questions, please drop us a line below. And if you want to see more videos like this in the future, please like and subscribe.
Hi everyone, today we'll be talking about indexing in databases. Specifically, we'll be talking about NoSQL databases. Hi everyone, today we'll be talking about indexing in databases. Specifically, we'll be talking about NoSQL databases because the traditional relational database indexing has been covered thoroughly. I have the links in the description below. Hi everyone, today we'll be talking about indexing in databases. Specifically, we'll be talking about NoSQL databases because the traditional relational database indexing has been covered thoroughly. I have the links in the description below. The main thing which is different in NoSQL databases is that there's the concept of a key. There's a concept of a hash that you're going to take. So you give it the key, it computes the hash, And based on this hash and the number of machines, it figures out which machine the record resides in. Okay, standard hash map stuff. Now in practice, of course, you're probably not going to be choosing the hash function. You're just going to pass it a string, and the hash function is good. It's uniformly random. So what you want is a good partition key. And an example of that is, let's say, user ID. The hash function makes them randomly fall on any one of these boxes. If you instead choose something which is quite generic, for example, gender, all males and all females being put together, if you have this channel, then about 90% of the people are going to be falling into one single machine. A good example of a partition key, like we said, is something which is random, something which is well distributed, something which is quite unique. The second thing that you want to do, if you are thinking about indexing in NoSQL databases, is to think of a sort key.
Repeat after me. An acre is the area of a rectangle whose length is 1 furlong and whose width is 1 cubit.
Key. If you are